All right, let's dive right in. Today, we're going to pull back the curtain on the digital world and get to the bottom of its biggest secret, the language every single computer uses to think, to work, to create everything we see. We're talking about its digital DNA.
And really, it all comes down to this one kind of mind-blowing question. I mean, think about it for a second. Everything our computers do, streaming our favorite shows, running these incredibly complex games, it's all built on the simplest possible idea, a switch that's either on or off. So how? How do we get from that simple flick of a switch to the amazing digital world we live in every day?
This really shows you the gap we're trying to bridge, right? On one side, you've got our world. It's full of color, it's dynamic, there's just endless information. But on the other side, that's the computer's reality. It doesn't see colors or hear sounds, it just sees a long string of two states, on and off. And we represent those with a simple 1 and a 0.
So, to figure out how a computer counts with just two little symbols, we've got to first look at how we do it with 10. Let's start on some familiar ground, shall we?
And this is it, the system we all know and, probably take for granted, the decimal or base 10 system. Why base 10? Super simple. It's built around 10 unique symbols, 0 all the way up to 9. It just feels natural to us because, it's what we've been using our entire lives.
So here's the key to how it all works. We have our 10 digits, right? But what's just as important is where a digit is placed. Think about the number 123. The 3 is just 3. But the 2 isn't just 2, it's in the tens place, so it's 20. And the 1 is in the hundreds place. It's all based on powers of 10. This is the language of all our everyday math.
But here's the catch. This system, which is so intuitive for us, maybe because we have 10 fingers, is just way too complicated for a simple electronic circuit. A computer doesn't have 10 fingers. It basically has one switch. It needs a much simpler alphabet, like an alphabet with only 2 letters.
And that brings us to it, the computer's true native tongue, the one it uses for absolutely everything it does.
So, say hello to the binary or base 2 system. Instead of 10 digits, it gets by with just 2, a 0 and a 1. That's it. This is the absolute bedrock of all modern computing. Every single piece of data on your phone, on your laptop, is, at its very core, just a really long string of these two numbers.
And this is where it all just clicks into place. See, binary perfectly maps to the physical reality of a computer's hardware. A 1 can represent a circuit being on, with electricity flowing. A 0 means it's off, no electricity. It's a direct one-to-one translation from the physical world to the digital. Each one of these digits is called a bit, and these bits are the tiny Lego bricks that build our entire digital universe. Okay, so this is perfect, right? We've found the ideal language for machines. Problem solved. Well, not quite. Because in solving the computer's problem, we've just created a brand new one for the humans who have to write the instructions for them.
And here's exactly why. Binary numbers get incredibly long really fast. Just look at this. The number 200, just 3 simple digits for us, explodes into this 8-digit monster, 11001,000. Now imagine trying to read, write, and find mistakes in code made up of thousands of lines of that. Yeah, it would be an absolute nightmare.
So the people programming these things, the engineers and developers, they needed a middle ground. They needed a way to speak the computer's language without drowning in an endless sea of ones and zeros. Basically, they needed a shorthand. And this is where octal and hexadecimal come into the picture. Now, the key thing here is not to think of these as totally new, complicated systems. It's much better to think of them as convenient, compressed ways for humans to read and write the binary that the computer is actually using underneath it all. They're like our handy translation guides.
Let's just quickly break them down. You've got octal, or base 8, which uses digits 0 through 7. Honestly, you don't see it around much anymore. But then you have hexadecimal, or base 16, and this one is everywhere. It uses 16 symbols, our normal 0 through 9, and then it borrows the letters A through F to stand in for the values 10 through 15. This is the one you'll see all over the place if you look under the hood of modern tech.
Okay, so we have all these different languages now, our decimal, the computer's binary, and this hexadecimal shorthand. How do they actually relate to each other? How do we translate between them?
This table makes it all crystal clear. Just look at the number 10 in our decimal system. For a computer, that's 1010.
But in hexadecimal, it's just a single letter A. And here's the real magic, the reason this works so beautifully. Because 16 is 2 to the power of 4. One single hexadecimal digit can always represent a perfect group of exactly 4 binary digits. So F isn't just some random letter, it's a super compact way of writing 1111. This is what makes hexadecimal such an elegant and frankly genius shorthand for binary.
So that's the theory, but what about in practice? Let's say you have a number in your head, a regular old decimal number, and you want to see what it looks like to a computer. How do you actually do that translation?
It might look a little intimidating, but it's actually just a simple recipe. First, you take your number and you divide it by 2. All you have to do is write down the remainder. It's always going to be either a 0 or a 1. Then, you take the whole number part of your answer and you do the exact same thing again. Divide by 2, write down the remainder. You just keep doing this over and over until you get to 0. And the final step? Just read that list of remainders you wrote down, but from the bottom to the top. And poof, that's your binary number.
Okay, so we've talked theory, we've talked different bases, we've even done a little bit of math. But let's get to the most important question of all. Why does any of this actually matter to you in your daily life?
Because this isn't just some abstract theory from a textbook. This stuff is the invisible architecture holding up your entire digital world. It's running constantly, right behind the screen in every single app you use and every website you visit.
In fact, you see it all the time, even if you don't realize it. You ever see a color code on the web that looks like a hashtag and then 6 letters and numbers, like hashtag FF5733? Yep, that's hexadecimal. It's just a compact way of telling the browser exactly how much red, that's the FF, green, the 57, and blue, the 33, to mix together to make a specific color. It's used for everything from computer memory addresses to file permissions.
And this quote from the source material really just nails it. This isn't just about math or computers. It's a fundamental part of how we interact with the world, both the physical one and the digital one we've built on top of it.
And that really brings us to the most incredible idea of all. Everything you see on this screen, every photo, every video, every complex and beautiful thing our technology can do is built from this simple 2-letter alphabet. It's just amazing what can be built from the ground up, starting with nothing more than an on and an off. So now that you understand the language, what else could you build with a simple 1 and a 0?